Hello everyone, today we are going to have the second episode on alcohol, phenols and ether. What I am going to illustrate today is about the chemical properties of alcohol. It would be easy to learn and mug up when we classify the chemical properties of alcohol under three subheadings. That is number 1, cleavage of RO and H. Number 2, cleavage of R and OH. And third to go is reaction of both alkyl and the hydroxyl group. So today's class will be more illustrating with equations and examples. So let us go with our next with this episode so that we will be learning more on the chemical properties of alcohol. Let's come back to the chemical properties of alcohol. As I have told you student that we can divide the properties under three subheadings. One is R, O and H. So if we make a cleavage between the hydrogen and the oxygen, this is one chemical property. The other chemical property would be R, O and H. So if we can make a cleavage between R and O. And the third is about R and OH when we are going to make a change on the alkyl group. So student, let us see how we divide under three subheadings. One is the cleavage between O and H. The second would be the cleavage between R and O. And the third is the change in the alkyl group or the reactions on the alkyl group. So here we have the first point, cleavage of R and H. So we are going to break the relation or the bond between the O and the H. So there is a bond between O and H. I am going to break that bond by some process. And you know that whoever can give out a hydrogen is called as an acid. So here alcohol, it shows acidic nature. So by these reactions, you can see point number 1, 2, 3, they are giving out that hydrogen so that they show the acidic characteristics. So let us see the first one, C2H5OH with sodium in the presence of ether. In the presence of ether, it is going to form C2H5ONa. So sodium, ethoxide and hydrogen. So hydrogen is evolved out. You can take any such kind of metal like sodium, potassium, calcium, magnesium, aluminium. Here I have taken aluminium and this is 3-degree alcohol. CH3, the whole 3, OH and Al. When you are passing it through ether once more, you can have the hydrogen gas. And hydrogen can be understood by the pop sound it forms when a burning splinter is brought near to it, and when you burn it in the presence of oxygen, it will burn with a blue flame. This is all. And now you can see here, I have given you an instance saying that the R in the ROH, that is the alkyl part in the alcohol group, is electron releasing. It is electron releasing. So this is electron releasing. R is electron releasing group. It increases the electron density on the OH bond. So what happens? This R, yes student, then this R, it releases electron and the electron density in oxygen increases. The electron density in oxygen increases, and if the electron density increases, OH bond becomes stronger. So you can see here, it increases the electron density on the OH bond so that OH bond becomes stronger and does not release H+. So if you see in case of the alcohol, if the R is of a higher magnitude, or I say the R is more than 5, it will be very impossible or rather difficult for that alcohol to release the hydrogen. So more the number of the carbon in this alkyl part, it will be less of acidic. Why? Because the OH bond becomes stronger and does not release the proton or the hydronium ion. So water is a better proton donor than alcohol. So water is more a better proton donor than alcohol. Alcohols are weaker acid. Water is also weaker. Alcohols are much weaker acids. And you can see here the number of R increases. As the number of R increases, greater will be the number of the electron releasing group, greater will be the electron density around the OH bond. So stronger is the OH bond and lesser tendency to release the proton. So lesser is the acidic character. So when you increase more and more alkyl group, like the plus I effect increases, and the plus I here means the alkyl group is more an electron releasing group, and this electron releasing group increases the density of electron on oxygen, and the bond formation between oxygen and hydrogen become much stronger, and when it gets stronger it will be difficult for oxygen to release the proton or the H plus ion. So you can see here, this is very important, CH3OH is quite more acidic than that of any other 1 degree alcohol, 2 degree alcohol and 3 degree alcohol. So as you can see, more the number of alkyl group, you can see electron density around the OH bond increases. So stronger is the OH bond and lesser tendency to release the proton, and so less will be the acidic character. In point number 2, we have the alcohol with sodium hydride. Sodium hydride or potassium hydride, it will help to give out the hydrogen gas. This is another way by which you can show the acidic character. There is number 3, Fischer-Spear esterification. Students, you have already learned even in class 10 very nicely about esterification. It was conducted first time by Fischer and Spear. So this is acid and alcohol. In the presence of sulfuric acid, it is going to form ester. It is going to form ester, E-S-T-E-R, ester and water. This is what we call esterification. The rate of esterification decreases with the increase of the alkyl group attached to the alcohol or the acidic part. So this is COOH, COOH and OH. So more is the, more the alkyl group you have on the alcohol and the acid, the esterification will decrease. So with more the molecular weight of the alkyl group, the esterification will decrease. It was first conducted by Fischer and Spear, and it is called as Fischer-Spear esterification. And you can see here, more the alkyl group, lesser will be the esterification reaction. Last to go on this part is the Schotten-Baumann reaction. Schotten-Baumann reaction. This is acetyl chloride, this is benzyl chloride. And when you are reacting this, these halides, the alkyl halides with this alcohol in the presence of sodium hydroxide or pyridine, you can use sodium hydroxide or pyridine. You can also get ester, and together with the ester you can get hydrochloric acid. It was called Schotten-Baumann reaction. And also here you can see the same thing. As the number of carbon increases, the electron density on the O part, on the oxygen part increases, stronger will be the bond and it will not form the ester. This is how we divide the alcohol on the cleavage between O and the H. Only some 4 reactions, first, second, third and the fourth. These 4 things you have to keep in mind. So if I go for the next one with the R, O and H, so now we are going to have a reaction between the alkyl group and the OH group. We are going to make a cleavage between the bond between the alkyl group and the hydroxyl part. So this is the main reaction that we are going to see now. In the second reaction, you can see this is the second part, cleavage of R and OH bond. The first is the group process. with alcohol and any kind of hydroxides with anhydrous zinc chloride, you can see that C2H5OH with HCl in the presence of anhydrous zinc chloride ZnCl2, it is going to form C2H5Cl plus H2O. So student, you know that ZnCl2 with H2O, this is what we call as Lucas reagent, Reagent. It is called Lucas reagent. So when you take this zinc chloride, anhydrous zinc chloride and hydrochloric acid, this is what we call as a Lucas reagent with alcohol. It is going to produce C2H5Cl and water. And now, who can show faster the reaction? It is depending upon HI. HI is more prone for this reaction than HBr and then HCl. And HF, hydrofluoric acid, will never show because the hydrofluoric acid is being bonded with a hydrogen bond, and because of the presence of hydrogen bond, they cannot escape out, it cannot escape out the fluorine atom. So hydroiodic acid is more prone to this reaction than HBr and followed by HCl. If you see the alcohol part, 3-degree alcohol show much faster reaction than 2nd degree, and 2nd degree can show much faster than the 1st degree alcohol or 1-degree alcohol. And this is the taste, you know, like we use in determining or to distinguish between the 1-degree, 2-degree and 3-degree alcohol. So 1-degree alcohol goes very late, 2nd degree it takes 5-6 minutes, and 3-degree it shows instantly the reaction. So this is the reaction that zinc chloride and hydrochloric acid. So anhydrous zinc chloride and hydrochloric, there should not be any water. So when you take anhydrous zinc chloride and hydrochloric acid with alcohol, they show the reaction. For 3-degree, it will be instantly forming. For 2-degree alcohol, it will be taking some 4-5 minutes time. While for 1-degree, it will take a lot of time. Even it is required that you heat it. Otherwise, the cloudy appearance of the precipitate will not be shown. Our next thing that we have to come here is about refluxing with alcohol. When you take, you know student, what is refluxing? So refluxing means first you have to heat it and then the liquid vaporizes, the vapor you have to cool it. This is one way you can go for refluxing. The other way is that you take the material and you just make it upside down, make into vapor and also heat it and then allow it to cool. It is also called as refluxing. So in the refluxing of boiling HBr, when you take C2H5OH and you take HBr, hydrogen bromide, and you take your concentrated sulfuric acid and you have to go for refluxing, Refluxing, refluxing. So you get here C2H5Br. So this Br joins here and water is formed. This is another way by which you can make bromide, iodide, and chloride, particularly with sulfuric acid undergoing refluxing. So again, if you go with C2H5OH and HI, hydrogen iodide, so when you do it, this is 57% purity, it should have 57% purity, and HBr should have around 40% purity, otherwise the reaction will not take place. So you can see here that it is forming C2H5I and H2O. Now the question is that we have to give here phosphoric acid, H3PO, phosphorus acid, say H3PO3, or you can use H3PO4, phosphoric acid. So ethyl alcohol in the presence of hydroiodic acid, in the presence of phosphoric acid, it can produce C2H5I and water. But if you use here red phosphorus, If you use a red phosphorus around a temperature of 423 Kelvin, you can see something different. What is that? It is going to give you the alkane itself. It is going to give you the alkane itself, C2H6 plus H2O, and you get your iodine. So this is how we also differentiate. When we give phosphoric acid, it gives an alkyl halide, and when you use red phosphorus at a temperature around 423 Kelvin, it is going to give you directly the alkane. This is the third reaction. The fourth reaction is called Dargen, D-A-R-Z-E-N, Dargen's reaction. Dargen's reaction. It is also very interesting that when you take that alcohol, say I have taken ethyl alcohol in the presence of SOCl2. This is called as thionyl chloride. This is what we call it as thionyl chloride in the presence of pyridine, Pyridine. In the presence of pyridine, what happens? One Cl, it joins with C2H5, so it forms a C2H5Cl. Another Cl, it joins with hydrogen to produce HCl, and this SO with this O, it forms here SO2. So remember student, this HCl is a gas, sulfur dioxide is a gas, so ethyl chloride what we get here is almost of 98% purity. So we always choose to go with Dargen's reaction in making ethyl chloride or ethyl bromide and so on. So student, this is alcohol in the presence of thionyl chloride, in the presence of pyridine, it is going to produce ethyl chloride, hydrochloric acid and sulfur dioxide. If we go for the next one, that is number I can say here number 5, as with C2H5OH and PCl5. When you go through PCl5, what the reaction you can see here is C2H5Cl plus HCl plus POCl3. You can also get ethyl chloride by heating it in the presence of phosphorus pentachloride. Number 6, here you have C2H5OH in the presence of PCl3. If you use PCl3 and heat it, you can see here 3 moles will take this 3Cl to form here C2H5Cl. So student, what is remaining? 3 hydrogen and 3 oxygen. So you can see here 3 hydrogen and 3 oxygen and 1 P, H3PO3. So you get your phosphorus acid. So student, here you can see how we can relate out the reaction. How can we relate out the reaction between ROH when we can have a cleavage between RO and H. So this OH is being replaced by the halide groups, and this is a very important reaction, particularly Dargen's reaction, because if you are to make ethyl chloride, you have to, or alkyl halides. This is the easiest process, and you get almost 10% purity because both of the compound formed as a product here will be evaporating out, will be vaporizing out. So the compound, the halides will be remaining in the product only. So it is very useful. So in our next episode, we will be going through. This is the third and the last chemical property for alcohol. So reaction between both the alkyl group and the hydroxyl group. So alkyl group and the hydroxyl group, there is a change. So let us see student, here we have two such different reactions. One is dehydration and other is the oxidation. So one is dehydration and other is oxidation. So this part only goes with dehydration and oxidation. In the dehydration part, we have divided into 3 subcategories once more. So this is concentrated sulfuric acid at 453 Kelvin. What happens is the H and the OH. So the H and the OH, from the alkyl part, the H and the OH part of the alcoholic group, they unite together to form here water. So they will be losing out water. they will be subtracting out water, and what the compound formed is an alkene. So you have an alkene in this reaction when you use H2SO4 or anhydrous Al2O3 also. It will work. So concentrated H2SO4 or anhydrous Al2O3, it will work to remove the water present within the alcohol and the alkyl group, the hydrogen part. Number 2, here you can see phosphoric acid in the presence of Al2O3 at a temperature of 298 Kelvin. So almost at the room temperature. You can see that they can either lose the hydrogen from here and the OH, or they may lose the OH and this hydrogen. So you have the two options. One is there is a loss of hydrogen and hydroxyl ion between these two, and you get here one butene. You get here one butene, and here you get two butene, B-U-T-E-N-E, butene. So this 2 butene is 76% and this is 24%. Now there is a rule here. This is called Side-Jeff rule. So Side-Jeff rule speaks here saying a more alkyl substituted alkene is always the major product. So here you see this is 2 butene and this is 1 butene. So 2 is more than that of 1. So 2 is more dominant. So this is a major product. 2. So if you have between 2 and 3 pentene, 3 would be more a major product than that of the 2 pentene. So when you have between 1 and 2, 2 will be more preferable. This is what the Side-Jeff rule speaks. I would always ask you to see once more and just you write down the Side-Jeff rule in your classwork copy. A more alkyl substituted alkene is more. So more alkyl substituted alkene. This is 2 butene will be the major product when an alcohol when a secondary alcohol or 2-degree alcohol is treated with phosphoric acid and a dehydrating agent like Al2O3 at a room temperature. And third to go is an alcohol with sulfuric acid, with concentrated sulfuric acid. If you give 140 degrees centigrade, it is going to form ether, and when you give 170 degrees centigrade to 180 degrees centigrade, you are going to get alkene and water. So you can see, student, that ethyl alcohol or any kind of alcohol with concentrated sulfuric acid at a temperature of 140 is going to give you ether. It is going to give you ether, and this it is going to give you alkene. So they are going to give you alkene, A-L-K-E-N-E, alkene. So it is going to give you alkene. Here I gave you an example of ethene. And this is all about the dehydrating property. And let us go on the oxidation now. So ethyl alcohol, when you are oxidizing it with K2Cr2O7 in the presence of sulfuric acid, here H plus means sulfuric acid. So you know, like sulfuric acid is a non-volatile acid. So in organic chemistry, we always prefer to take sulfuric acid because of its dehydrating property, oxidation property, as well as that it can be non-volatile. So here it forms to aldehyde, and aldehyde on further oxidation, that same K2Cr2O7, same K2Cr2O7 in the presence of the acid, it is going to form the acetic acid. So ethyl alcohol to ethanaldehyde or acetaldehyde, and this acetaldehyde to ethanic acid or acetic acid. But if you use copper turnings at a temperature of 473 to 573 Kelvin, it is going to form aldehyde, that is ethanol or acetaldehyde, and the reaction stops. It will not go further. That means with copper at 573 Kelvin, you cannot form acid. So you are going to form aldehyde. So when you are going to prepare aldehydes, be sure that you are using copper turnings and not K2Cr2O7, because K2Cr2O7, once it forms aldehyde, it will oxidize further aldehyde to acids. And here I have given you 3 examples. One is of 1 degree alcohol, this is 2 degree alcohol, and this is 3 degree alcohol. So this is 1 degree, this is 2 degree, and this 3 degree alcohol. For 1 degree alcohol with copper turnings at 573 Kelvin is going to form aldehyde. it is going to form aldehyde. With secondary alcohol, it is going to form ketones, K-E-T-O-N-E-S, ketones. So primary alcohols, when you are treating with copper, it is going to form aldehydes. And when you are taking secondary alcohol with copper turnings at 573 Kelvin, it is going to form ketones. And when you take 3-degree alcohol with copper turnings at 573 Kelvin, it is going to form alkene. It is going to form alkene, A-L-K-E-N-E, alkene. So, an interesting fact is that this is a very important reaction because it helps us to distinguish between primary, secondary and tertiary alcohol. So if there are questions coming up in your examinations regarding how you are going to separate primary, secondary or tertiary or 1 degree, 2 degree and 3 degree alcohol, I think this is a better opportunity to use this type of reactions. Why? Because aldehyde is going to show you Schiff's reagent. It is going to show you positive to the Schiff's reagent. It is going to show you Tollens reagent. It is going to show you Fering's test. While ketones, they will not show you the reaction on the Schiff's reagent. It is not going to show you the Tollens reaction and it will not show you Fering's test. And the 3-degree alcohol, you know that students, this reaction will show you with an alkene, and being unsaturated, they are going to turn the bromine water, the red bromine water, colorless. Or with K-manophore, pink color K-manophore, this pink color K-manophore will also get decolorized with this reaction. So student, this is how we are going to differentiate between the primary, secondary and tertiary alcohol. This is all for today. Hopefully you have understood how we are going to classify the chemical properties of alcohol on 3 bases. First is the cleavage between RO and H, number 2 between R and OH, and number 3, this is the reaction between both the alkyl group, and the hydroxyl group, alkyl group and the hydroxyl group, alkyl group and the hydroxyl group. This is how we do it. And the third reaction, it has got 2 more aspects. One is dehydration reaction, another is oxidation reaction, and we have categorized into 4 different types. Four different types of examples being given, and this reaction is particularly being given to differentiate between primary, secondary and tertiary alcohol.